of regularization, which is also extremely common in the literature. It's called the LASSO regression. So what is the difference between the LASSO regression and the ridge regression? It's just the norm that I'm using. In the ridge regression, I'm using the 2-norm square of the solution. But in the LASSO regression, I'm using the 1 norm, L1 norm. And it is defined as the sum of the absolute values of the vector. Okay? So why do I want to study this problem, and how does this L1 norm solution buy me some benefit? Well, it turns out that if you have a fat matrix, that's usually for fat matrix, you have a lot of feature vectors. But think about in a typical scenario, how often do you need to activate all these feature vectors? Probably not. You have 10,000 feature vectors. Maybe only 100 of them are playing an active role in making the prediction. And the 9,900 of them, they don't really matter, right? So if that is the case, then you want your solution to have a bunch of zero numbers, zero entries, and then you want to have a few entries that are non-zero. Okay, so instead of just constraining the magnitude of all these numbers, you actually want to control the number of non-zeros in your vector. Because if you do that, then you can guarantee that only a few columns in the A matrix, they are activated. And the rest, you can just say, okay, they're zero. They have zero contribution to my prediction. That's actually a good thing, because you can do interpretable analysis. You can see what features are important. And then your solutions would be very, very dense. And you can also do dimensionality reduction, because then you can throw away the unimportant feature vectors. So it's a very useful thing to consider. So why does this L1 norm help you to achieve that goal of picking a few numbers of non-zeros? You can view it through the following diagram. So what is a 2-norm square? Well, 2-norm square, you think about it a little bit more, is actually drawing a circle. Okay? 2-norm square on theta is drawing a circle. Okay? And then now if you have an objective function which tries to make it as low as possible, then what you're trying to do is that you want to find a solution that the two circles, they will intersect. Okay? And when they intersect, you have a solution that can be anywhere on this plane. Now, what is the 1 norm? The 1 norm, if you draw it out, is a diamond. It's a very interesting structure. It's a diamond structure. So when you do the same thing, you try to minimize certain objective function, and then when it hits a diamond, well, you have to hit one of the 4 vertices. Right? 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 Okay. So if you hit one of the 4 vertices, then one axis should be 0, the other axis should be 1, or some number. Okay? If you're at that corner, then the first axis is some number, the second axis will be 0. Okay? So since you're hitting the vertices, you are guaranteed to have a lot of numbers are 0, and then only a few of them, they are non-zero. Okay? Now you can extrapolate this idea to high-dimensional spaces. It's the same phenomenon. That's why when you try to minimize this L1 norm problem, you're guaranteed to get a sparse solution under a set of conditions, of course. Okay, and so this is the philosophy behind LASSO, which is to find a set of sparse solutions using a 1 norm. Now, when you look at this problem and say, holy, this is a L1 norm, okay? This is absolute value. How can I take derivative set it to 0? Yes, you cannot take derivative to 0, okay? It's not differentiable at 0. And so you're running into some trouble to find an algorithm to solve that problem. That's the whole business behind the literature on convex optimization, because you realize that this is a convex function. We will talk about what convexity means next time. So you realize that this is a convex function. That means you will have some optimization algorithms out there that can solve convex optimization. that can give you a solution of this problem. Okay? It's a lot harder, but it's not that bad. Okay? So if you're still thinking that the cutting line between difficult and easy problems being linear and nonlinear, that's not the case nowadays. It's between convex and non-convex problems nowadays. Convex problems, you can solve it in polynomial time with well-designed algorithms. Non-convex problems, most of them, you cannot solve it in polynomial time. They're very, very hard. Okay, so how can sparsity be useful? The sparsity is actually very useful beyond just selecting a few features. It's actually very common in images. If you take an image, you go to certain domain, like Fourier domain. Fourier domain is not the best domain. Go to the wavelet domain, okay? Go to the wavelet domain. Now, how to do wavelet domain? Go to NumPy, there's a signal processing toolbox, and there is a wavelet command, do a wavelet transform of the 2D image. Or MATLAB, there's equivalent command of doing the wavelet transform. So go to the wavelet transform. What it does is that you have a bunch of wavelet bases, and then you try to project the image onto all these wavelet bases, and then you get the coefficients. So these are called the wavelet transforms. Okay? So once you get these transforms, you look at these numbers, you realize that, actually a lot of these wavelet coefficients, they are extremely small. They're so small that even I make them to 0, I'm good. What do I mean by good? This is an example showing you here. On the left, this is an image with only 33.5% of the coefficients, they are non-zero. The rest 67%, they're 0. I just truncate them. I just make them to 0. You can still see the image pretty well. Okay? Now, if I go down the non-zero percentage to 13%, I can still see a pretty good image. Even if I go to just 1% of the entire image, okay? So the entire image could be a megapixel image, and then that means you have a megapixel variables. I throw 99% of them away, just use 1%, I can still get a decent image. It's not that good, but it's still there. The content is still there, okay? That means natural images, they are pretty sparse in a domain, in that transform domain, which is called the wavelet domain, or you can just make that A matrix, all the columns being the wavelet basis, okay? This is actually the principle behind all these JPEG 2000 ideas, okay? JPEG is discrete cosine transform, JPEG 2000 is wavelet. That's the only difference, okay? So it's being used for decades in our technology history, okay? So sparse model is very useful. People have been using it for other tasks like image denoising, image inpainting problems like these. So on the left, you see the image that is corrupted by missing pixels. You have 80% of the pixels that are missing. And then you apply this sparse representation since you know that the signal only has a few non-zero elements that is enough to represent the image in certain domain. You can just solve an inverse problem to get the image back by finding all these non-zero elements. You can do the inpainting, like where you have some text that's covering the image. You can remove them. Okay? So this is a very classical paper that was published about 10 years ago that talks about how to design a good basis matrix to do these kind of problems. Okay? They are all based on the same principle. In different communities, they call different things. Okay? In statistics, you call it LASSO. And then in signal processing, there's a set of techniques called the basis pursuit or orthogonal matching pursuit, that kind of algorithms. So you have different variations of that same idea of exploring the sparsity of that vector. So one of the underlying key component of this LASSO operator is this shrinkage thing. Okay. So what is this shrinkage operation? The shrinkage operation is an operation that solves an optimization without the A matrix. Why do I want to study this problem? Well, because you need a shrinkage operator to put into a set of algorithms in order to solve that original LASSO problem where you have the A matrix. Okay, so how do I solve this lasso problem? Well, you look at this equation, you realize that in this problem, of course, there's no A matrix there. Right? Remove the A matrix, set it to identity. Then, what is this? Well, the first equation is just the sum of all the square terms, and then the sum of all the absolute terms, as I'm showing you here. If you're not following, let me just remind you, the 2 norm square is the sum of the squares, and then the 1 norm term is the sum of the absolute values. If I just write it out, it will look like this. Okay, it will look like the second equation on the slide. Okay, so since this is a summation of individual terms, and all the individual terms, they are what? They're positive, non-negative. Okay, that means by minimizing individual terms, I can minimize the overall sum. Think about the sum of positive numbers. If each positive number is minimized, that means the sum of all these positive numbers will be minimized. Okay? So I can just look at one small problem there, which is just containing the scalar problem, where you have this y and theta square, and then you take a 1/2, and then there is a lambda and absolute of the theta. This is a scalar minimization problem. It's a one variable minimization problem. Now you can say, can I take derivative set it to 0? Sort of. Okay. So what we can do is that you can kind of take the derivative set it to 0, and then you will get a solution. Okay. So let me quickly show you how you can do that, because you may see this shrinkage operator very, very often in the literature. Okay, I promise. Okay, and so it's important to get at least once in your lifetime exposure to how do you show this result. Okay, so let me quickly go into the last page of this appendix. Okay, in the appendix you have the full proof, but let me just quickly draw some diagrams for you. All right. Okay, so you have this function of this j of theta, which is 1/2 of y minus theta squared plus lambda of theta. Okay, this is a scalar problem. It's a scalar problem. So what you do is that you can take the derivative of this j. Let's pretend that you can take the derivative, although some of you are here. How can you take the derivative of the absolute value? Let's bear with me, okay? So let's take the derivative. Then what do you get? Well, you get y minus theta, okay, with respect to theta. Then you have a lambda. Okay, so how do we take the derivative of this theta? Well, it depends on the sign of this theta, okay? Because if this is a theta, then this is absolute theta. Okay, so that's the plot of the absolute value. And so if we take the derivative, what will it become? The slope. Okay? So the slope on the positive side is 1. The slope on the negative side is -1. The slope of that function. Okay? So what it is? Well, it would be the sine of the theta. Okay? It's either plus or minus. And if you're at 0, it can be anything. That's just the definition of the sine function. All right, so now we can run into this. You have 3 cases. You have y minus theta, and then y minus theta, and then you have plus lambda. Okay, and then this is a case when theta is bigger than 0, and then that would be the minus lambda when theta is less than 0, and then there will be y minus theta when theta is 0. Okay, and if theta is really 0, you don't have a problem. Okay, because in the second case, since you know that theta is 0, then the solution is theta is 0. So let's look at these two. So let's look at this case and then this case. Okay. So how do I? Okay, I need to insert slide blank. Okay. So what is it? Well, you can consider 3 cases. So you can say that if my theta is positive. Okay, then what do I have previously? Well, previously you say that y minus theta plus lambda is 0. Okay, so go back to this equation here. you see that, okay, if this is 0, then you have this equation. And so you will have y minus theta equals plus lambda equals to 0. And so you will have theta equals to y minus lambda. But since your theta is positive, because of the assumption making here, then you must have y bigger than lambda. Okay, and it has to be bigger than 0. Okay, now you can do the same exercise for the next case, where if your theta is negative, then you have this theta will equal to y plus lambda. And since this is less than 0 now, then you have y less than minus lambda. And this is less than 0. Okay? And so if you put everything together, you will get the following results. You will have this theta hat. That would be what? Well, that would be, okay, that would be either one of the three cases. It would be either y minus lambda or y plus lambda, and depending on the value of the solution. So you will have y minus lambda and then y plus lambda. And then the first case will happen when y is positive, when y is negative. And if y is indeed 0, then you just get a 0. That's how we can get the shrinkage operator. Okay? And then if you do some work here, you can actually show that this theta hat is indeed this operation of maximum of y minus lambda and 0, and then times the sine of your y. Okay? Now, how can you do that? You just assume the case y being positive, y being negative. Just expand this maximum operation. You will see what I mean. Okay? So, this is the one-page proof of the shrinkage operator. The shrinkage operator will have a shape like this. Okay? It's also called a soft threshold operation. And this soft threshold operation has a range of plus lambda and minus lambda, within which you will get a 0 solution. And after that, you will just shrink by that magnitude, and then take the sign. Okay? Now this is very different from another thing called the hard threshold, where you just have a line and truncate whatever that's in between plus lambda and minus lambda. Now, if you have any experience with deep neural network, you realize that there's a thing called the ReLU, okay? Rectified linear unit, okay? This is actually one side of that shrinkage operator, okay? And of course, there's a shift towards the 0. And so this ReLU thing is not that magical, okay? So if you go back to the one layer case, and then you have some kind of thresholding operation going on here, it's all about this one norm minimization problem, which you can draw some interpretation from there. Now, of course, the difficulty of deep neural network nowadays is that you cascade multiple blocks together. That would make the analysis a lot harder, okay? But if you're only looking at one block, then essentially what they're doing is this kind of shrinkage and then finding the right basis, projection, these kind of operations. Okay? That's why we want to spend some time understanding all these linear operations before we move on to the more complicated deep neural networks. In the literature, you can find tons of algorithms to solve this LASSO regression problem. I'm just listing 3 of them here. The ECE algorithm back in 2004, the FISTA algorithm 2008. If you want something more recent, that is the ADMML from 2011. But this is like more like a reinvention of what people have found a long time ago, back in the 1990s. In fact, if you trace back, ADMML algorithm was founded in the 50s. Okay? So there are lots of these algorithms that can help you solve this LASSO regression algorithm with the A matrix present. If you look into all these algorithms, you see that they are iterative algorithms. In each step that involves some calculation of the inversion through the A matrix, like the pseudo-inverse that we have been doing. And in addition, there will be a shrinkage operation. Shrinkage operation meaning that you have a maximum, you look at the magnitude, you look at the sign, that kind of operations, and then do it iteratively. Okay. Now, how many iterations do you need? That really depends on the specific algorithms that you choose. Okay? So for LASSO, unfortunately, there is no easy solution. You need to use an iterative algorithm to solve. So for the remaining 2 minutes and so on, let me just comment on one very practical example. This is a data set that I obtained from a textbook on statistical modeling. And so you can look at this data sets. There are 50 cities, and then they're looking at the crime rate data. There are 5 columns in this data set, and they are the funding for police department, number of residents, they have the high school degree, and so on. And then there are some scores, which we don't want to spend too much time interpreting the meaning of the scores, okay? So there's a bunch of scores. Let us try to solve this regression problem using 2 approaches. One is using the ridge regression, where you have the lambda. One is to solve using the one norm, which is the LASSO problem, and see what do they behave as you change the lambdas. Now, I'm not too interested in solving the unregularized solution, because that would just be one special case when you set lambda equals to 0. Okay? Okay, so then you can try to plot the function, the solution, which is a solution, where the solution will contain all the 5 coefficients. You track them over different lambdas. Okay, for every lambda, you solve this problem, and then you find out all the solutions for different lambdas. The one that I'm showing you on the left is the ridge regression result, and then the other one is the LASSO regression result. They are substantially different in terms of this trajectory of the 2 solutions. What can I comment on these 2? Well, if you want to use the ridge regression, at any instant point, you will get almost all these features being activated. You look at any instant of the lambda, okay? Almost all the features are activated. But if you look at the LASSO, you go from a big lambda to a smaller. Big lambda means that you want to make sure that there are only a few non-zeros, very few non-zeros. So go from the right to the left by decreasing the lambda values. You can see that one of the feature vectors is activated first, right? So that means which one? The green one, okay? So the green one, if I can only allow you to pick one feature vector, what will it be? The green one seems to be the more reasonable one to pick. If I allow you to pick 2 feature vectors, then according to this LASSO analysis, you may want to consider picking the green and also the blue, right? So this perspective is only offered when you have this selection process given by the LASSO regression. If you try to do the ridge regression, yes, you do gain the benefit of having an easier solution, but you may lose some of the interpretability of your results. Okay? So that is the difference between the L1 norm versus the L2 norm analysis in terms of analyzing data sets. The last slide is just to comment on the positives and the negatives of the ridge regression and LASSO regressions. Okay? So there are different benefits of the ridge, which especially you have a lot more analytic tools to analyze the performance. The LASSO one, however, nowadays is no longer a problem given the availability of all these convex optimization algorithms. In addition, it offers you some additional interpretability results. Okay. Now, of course, if you know I'm not a big fan of algorithms are still harder than a ridge regression. That is the only drawback I can see for now. Okay. All right. So this lecture concludes here, and then next time when we come back, we will understand there's a prediction model, there's a loss function here. How do we extract the features? Okay, so next lecture will be the first exploration to the feature space. Okay? So I'll see you there.